I'm recording. Today we're going to be completing the review, the practice review for our first exam. The first exam is online you take it through Canvas. There's an hour and 40 minutes allotted for the exam, but just so you know, there's only 13 questions on it. Okay, so an hour and 40 minutes should be fine, okay, as far as the amount of time you need. You can use your notes, whatever you've taken for the exam. Just please don't use each other. Okay, that's my request. Let this be kind of a representative to you of how well you can, manipulate these concepts on your own. Now, the other thing you have to realize is the program that I'm using for exams and homework and things will automatically grade your exam, but that's not your final grade on the exam. There are directions that come with the exam that say, upload your work. Okay, there are for those of you who don't have a scanner, there are some apps that will let you take a picture and make a PDF out of your work and send me your work. Okay, and then I will go through and regrade the exam and give you partial credit. Okay, but again, like any exam you would take in class, you're going to need to show your work. So when you sit down to take the exam, first of all, make sure you have an hour and 40 minutes set aside to do it. Okay, the exam is structured so it can't be reopened. All right, and then make sure you're able to, write your work down on a piece of paper that at some later time you can either scan in, take a picture of, and then send to me. Okay. Does anybody have questions about the exam? Okay, this is kind of like our first unit exam that we would have taken in class had we been meeting in person. Okay, questions about the exam? Again, the directions that are, at the beginning are pretty straightforward. Okay, but this is your opportunity to ask, and it's due Sunday at 11:59 p.m. Please do me a favor. You have an hour and 40 minutes. Okay, don't start the exam at like 11 o'clock. You won't have enough time to finish. Okay, the exam automatically closes when the time limit is up. Okay, so what you need to do is give yourself enough time set aside. That's difficult for some of you, especially those of you with small kids. But there aren't that many of these exams in the class. So please try to make arrangements. And as always, if you're struggling with anything or this isn't working for you, reach out, let me know that, okay? All right, so the exam is over. Question in the chat. The exam is over all the material we've covered so far. It's basically like what we're doing in this practice session, okay? So let me start sharing with you, okay? Share okay, just to make sure everybody is aware of what we are using to go over this. So here's our course, all right? Here's week 4, which is where we're in. I am using this practice for exam 1. We did half of it on Monday, and I'm going to finish the other half of it today, as well as take any specific questions you might have, okay? Here's the exam, okay? So here's what you want to do by Sunday at 11:59 p.m. Okay, so again, I need to start my iPad. Again, this takes a bit, and it's kind of hard to do it in advance. So please bear with me while I do this. So let me share that with you. Right, everybody should see the practice problems where we left off, okay? And again, you can see we're down here. The last one we did was the limit problem on number 13. So we're going to be starting with number 14. Okay, again, I'll keep the chat open. So if you have, okay, another question in the chat was, is there a specific day we have to do the exam? No, it has a due date of Sunday at 11:59 p.m. So you have to do it anytime before then. Okay. And again, just set aside an hour and 40 minutes for yourself. That's going to be the hardest thing, is setting aside enough time in one piece. Okay. Anybody, before we move on, any other questions about the exam? Okay. All right. Okay. Then here we are. Let's get started. Okay. We're going to pick up with the limit stuff that we did last time. And again, it goes along with this graph right here, which is hopefully large enough for you to see. Let me get rid of my start here Wednesday, and we can move on. Okay, so the next question here, the next limit question, is asking you, what is the limit of f of x as x approaches 0 from the right? Okay, so limit as x, yep, x approaches 0 from the right. Okay, and again, I kind of want to make sure everybody is clear with these limit type graphs. Okay, from grading the one example in your homework where you had to draw the graph, I would say about half of you understood what to do, the other half not so much. Okay, so this is another opportunity to ask questions about how this works. Okay, so in this example, we're interested in approaching 0 from the right. Well, if I'm approaching 0 from the right, the only part of the graph that's approaching from the right is right here. Okay, so you can see as I get closer and closer to x equals 0, which is the y-axis, from the right-hand side, that's what the positive sign means here. Okay, I'm approaching what? Am I getting closer to what's happening to my y values? Okay, so I'm getting one answer that says infinity. Okay, they're increasing. And the point is they are increasing, but they're increasing without bound. Okay, so f of x, okay, without bound. Okay, another way to say that is to say it approaches infinity. Okay, it approaches infinity. So you could say that the limit, okay, as x approaches 0 from the right is infinite. Okay, it approaches infinity. You can see that given this graph, there's a vertical asymptote at x equals 0, right? The blue part of it at the bottom is approaching negative infinity, the blue part of the graph, and the pink part that I just drew is approaching positive infinity, just like an irrational function. Okay, so part of this graph, part of this function is rational with a vertical asymptote at 0. Okay, anybody questions on 14? Okay, let's take a look at the next one. Now, what's important to realize about the next problem is they're saying the limit as x approaches 0. Notice there's no positive or negative sign, okay, on that x value. So they're asking you all together, okay, what's happening when x approaches 0? Well, again, we can see the bottom arm of this graph right here is heading towards negative infinity as it gets closer to x equals 0 from the left. This arm is approaching positive infinity as x gets closer to 0 from the right. Okay, so what can you say about the limit as x approaches 0? What do you think? Okay. Remember, one of the criteria for limits is in order for the limit to exist, neither of the limits as you approach it from the sides can be infinite. Okay. Also, the two values as you approach it from the left and the right have to be the same. Okay. So I would agree with Cecilia, and I would say this limit does not exist. Okay, does not exist. Okay, does everybody see how I'm doing that? Okay, anybody questions on 15? Questions so far? Making sense? Okay, let's take a look at the last limit question, which is question 16, and that's the limit as x approaches 2. Okay, so where is that? Let's take a look over here. I'm going to get rid of this pink drawing here on this part of the graph. Okay, you can see that x equals 2 right here. And you can also see the function isn't defined there. See the whole? I mean, it is defined, but it's not the same value as what the limit is, okay? So the value of f of 2 is 3. Okay? And the limit as approaches 2 from either side is different. Let's take a look. Okay, as we approach it from the left, you can see the y values are approaching 1. As we approach it from the right, you can see the y values are approaching 1. So even though the value of the function isn't 1 when x equals 2, okay, you can see the limit as we get close to it is 1. Okay, everybody comfortable with the limit being 1? Okay, I have a question, which says, how does it equal 3? Okay, see the dot up here over x equals 2? There's a hole in the smooth part of the function, okay, right at x equals 2. And the value of the function is up here at 3. Okay, that's what this displaced dot means. Okay, so the function is continuous, not continuous, but it has a domain that goes pretty much, let's talk about that for a minute. This function has a domain of all real numbers except what? Okay, what's the domain of this function? Maybe that'll help. What's the domain of this function from the graph? Take a minute and look at it. Okay, what's the domain? Can anybody see if anything's left out? Okay, you want to assume, by the way, there's an arrow over here that goes out. Okay, so how do you do this? Okay, we have some guesses. Now remember what domain is. Domain is the x values for which f of x has a defined output value. Okay, so let's take a look. What I'm going to do to answer the question is I'm going to write on the function, starting at the left and moving to the right. So I'm writing on this function. This goes all the way out towards negative infinity. Okay, and then I'm coming in over here, and I get to this hole, and you might say, the function's not defined at negative 2, but it is. See the solid circle here? Okay, in this function, when x is negative 2, f of x is 0. Okay, and then you can see I go down, down, down as I'm getting closer and closer to x equals 0. Am I ever going to reach x equals 0? on this arm of the graph? Okay, no, as I go down, I'm getting closer and closer and closer to it. Okay, but I will never reach it. Likewise, on this arm of the graph, okay, jumping across this asymptote, you can see I'm going to get closer and closer to x equals 0, but I'll never reach it. Okay, so that means x equals 0 is not in the domain. Okay, now let's keep traveling on the graph to the right. You can see I get here to this +2 and there's a hole, but there is a function value there. It's just not continuous, right? See how it's displaced? And then you can assume as I go out on this arm of the graph, I'm going to hit all of the positive numbers to the right of 5. Okay, so the only value of x that's not in the domain is 0, where the asymptote is. Okay, even though you've got a discontinuity here, a jump discontinuity, and you've got a hole here, okay, there are values of the function there. Okay, so does that help answer the question about why is the value of the function 3 here? Okay, this is called a discontinuity. It doesn't mean the function isn't defined at x equals 2. Okay, some questions? Okay, ask again if it's not clear. Okay, not getting questions. So here's what we'll do. Let's continue with the rest of the review just to make sure we cover everything. And then I'll come back and I'll ask again if you want to do some more limit stuff. Okay, because again, I know from experience that this is a shaky concept. Okay, so again, moving on, let's take a look at number 17. Now, these are limit questions that involve algebra. Okay, so I'll try to work in the space that I have here, but I'm just saying sometimes it's going to be a little tight. Let me draw some lines to separate these. And again, you don't necessarily always have to do algebra to answer these questions. You can even use your graphing calculator to answer these questions. In other words, graph it and see what happens, okay, as you get closer and closer to the x value in question. Okay, some of this stuff you might recognize from what should I say, from college algebra. Okay, like for example, you can tell if I plug in, most people say, well, in order to figure out a limit algebraically, just plug in the value that's given. Okay, so let's look at this denominator and see what happens if I plug in -3 for x. -3 squared is +9. 2 times -3 is -6, minus another 3 is -9. So +9 minus 9, I have a 0 down in the denominator. So I can't just plug in the x value. Okay? What you need to do when you have polynomials, this is a rational function, folks. And what you need to do when you've got polynomials like this is factor your numerator and denominator. Okay, let me put something useful in the chat. There are factoring apps online. Okay, so again, type. Okay, there are factoring apps online. Type in algebra factoring calculator. Okay, you should have this skill, but in case you don't, you want to leverage technology. If you put in factoring calculator, it might just give you a number factoring calculator. So that's why I use the word algebra. Okay, so let's do this over here. If I look at my numerator, I recognize the pattern. I should recognize the pattern of difference of squares, right? X squared is a squared term, 9 is the square of 3, okay? And that factors as the sum and difference of the square roots, okay? So x is the square root of x squared, 3 is the square root of 9, and you write the sum and difference of those two terms, okay? The denominator might be a little harder to factor, okay? Remember how you factor polynomials? You look at the sign here, okay? This sign basically tells you, the negative sign in front of the last term, says that you have two factors, okay, and the signs in them are mixed. Okay, that's how you get a product for your last term that's negative. Okay, so I can tell since this first term is x squared, I've got an x here and an x here. And then I'm looking for two numbers that multiply to give you -3 and that add to give you +2. +2 is this here. Okay, it's essentially the term in the middle. Okay, you might remember there's only one way to multiply integers. Okay, well, actually, there's two ways to multiply integers to get -3. -1, +3, +1, -3. But since when you add them, you want the sum to be positive, then the bigger number has to be here. Okay, so is everybody okay with that? Everybody seeing what I'm showing you? Okay. Now what you can do is you can do what they told you not to do in college algebra, okay? And they told you this because they didn't want you to misconstrue what you were looking at. Notice you've got two terms that match. You've got the x plus 3 over the x plus 3. That means there's a hole in this function at -3, okay? So that's a hole. There's also a vertical asymptote at x equals 1. So the terms in your denominator, the factors, give rise to holes and vertical asymptotes. How do you know which is which? Well, if there's a match in the numerator, it's a hole. If there's no match in the numerator, it's a vertical asymptote. This factor in the numerator tells you where the function crosses the x-axis. This graph will cross the x-axis at x equals 3. Okay, so I can tell that just from looking at the factored form of the function. But what I'm going to do here, because I'm taking a limit, is I'm going to cross out the common factor. Now what I have is the limit as x approaches -3 of x minus 3 over x minus 1. That's what's left. Okay? And again, now that I've gotten rid of the problematic term, let's just plug in -3 for x. Okay, that gives me -6 over -4. And again, you have a calculator that can probably reduce fractions if you've got a TI-84. Otherwise, you'll remember negative divided by negative is a positive. And I can divide a 2 out of the 6 and out of the 4. Okay, so my limit here is 3/2. Okay, so questions about 17? Again, if you don't want to type in the chat, you can unmute yourself briefly and ask a question. Okay. All right, we're good with that one? Okay. Excellent. All right. Let me see. What we can do, right, is with the next one. Okay. I'm sorry, I'm getting texts from students who are not being able to get in. Let me just get back to that. Excuse me, just a moment. All right, I will get back to you in a second. Okay, so this next one, okay, is kind of weird. Okay, you might remember sum of cubes. From factoring land. Okay, remember sum of 2 cubes. And I want to think that went like this. It went a cubed plus b cubed. And then there was a factoring pattern for it that went something like, let's see, we started with the same sign. So it was, let's see, a plus b. And then you had b squared minus ab plus b. I'm pretty sure that's the pattern. Okay, everybody remember this pattern. Okay, if you've got 2 cubes, okay, it factors as, okay, and you're plussing them. You have the cube root of each with a plus, and then it's a squared minus, the sign flips on the middle term. Then the product of the 2 values, and then b squared. Okay, so how can we apply that here? I thought of it because I saw the cube symbol here. And again, I know that 1 is a perfect cube. 1's a perfect square, it's a perfect cube, it's a perfect fourth, it's a perfect everything. Okay, so that's what made me think to use that. So what I can say is, let's let a equal what's in parentheses, h minus 1. And let b be the cube root, which is 1. Okay, so I've taken the cube root of both of the things in the sum of cubes, right? Cube root of h minus 1 cubed is, well, h minus 1. Cube root of 1 is 1. And then it's a matter of just rewriting this so I have those things in there, okay? So here's my a plus b, the first factor. So I have h minus 1 plus 1. That's my first factor. Okay, and then I have a squared minus ab. Okay, so ab is just the 2 of them multiplied together, plus the last term is always positive. Okay, so that's what I've done with the numerator over h. Now you might look at the limit and say, why are you factoring the numerator? The problem is the 0 in the denominator, right? If I substitute 0 for h, and I know that's the problem, but what I'm hoping is maybe an h will fall out of all of this stuff in the numerator, and I'll be able to cancel out the h in the denominator, okay? So the idea is to see if we can factor out an h, okay? Everybody understand the strategy, okay? With these algebra-based limits, there has to be some kind of a strategy, okay? So let me continue on here. Okay, if you look at this h minus 1 plus 1, you see, lo and behold, there is an h. Okay, so this is h. And then this whole business again, which I'm not going to factor out. I'm just going to leave it like it is. Okay, and I'm simplifying a little. 1 times h minus 1 is h minus 1, and 1 squared is still 1. But here's what I wanted to have happen. See the h in the numerator and h in the denominator? There you go. Okay, and I've just gotten rid of the problem. Now I can take the limit as h approaches 0 of this quantity in the numerator. Okay, and that just involves substituting zeros for the h's. Okay, there's no denominator anymore, so let's see what we've got. This is the limit. Okay, and again, plugged in the value, so I don't have to take the limit anymore. I plugged in the numbers. Okay, let's see what this gives us. Okay, this is -1 squared, that's a 1. Okay, this is minus a -1, so that's a +1, plus another 1. So this limit equals 3. Okay, so again, you can see this limit is equal to 3. Okay, questions on 18? Okay, so again, if you're presented with something algebraic, you try to manipulate it algebraically to see if you can get rid of the problem with just plugging in the x value here. Okay. Also, another alternative is to graph the thing and see what happens as h gets close to 0. You should see with this graph that the graph itself will get close to 3. Okay, shall we look at the graph? Shall we look at the graph? Anybody want to see the graph of this? Okay. Again, it's a good idea to have multiple strategies, okay? Particularly if you're, trying to work on an exam. So let me bring up Desmos and let us put this into Desmos. Okay, so again, I'm going to try to have y equals, and I'm going to put my numerator in parentheses since it's a fraction. Instead of h, I'm going to use x because that's what comes. Okay, so there's my first term in the numerator, and then I have a +1. And then here's my denominator, x. Okay, so that is comparable to h minus 1 cubed plus 1 over h. And again, what they want to know is what's happening as x is getting closer to 0. Well, if you actually look at 0 over here, let's see if I can get close to 0. Okay, you see it's undefined right there. Okay, that's because the h factored out of the numerator and denominator. There's a hole in the function there. But you can see, where is that hole? I'll move slightly to the left. Oh, hey, the y value is close to 3. Move slightly to the right. Hey, the y value is close to 3. Okay, so that's how you can see the limit in the graph. Okay, so I'm asking you a question. See the limit in the graph as x is close to 0 on both sides. You can see it's close to 3 here and close to 3 on the other side. See the limit? So this is an alternative way to doing a whole lot of algebra. Okay, now, if you do this on the exam, something like this on the exam, please do me the favor of saying, I graphed it in Desmos and saw this. Don't write me a paragraph, just write me a sentence or two that lets me know you knew what to do, okay? By telling the limit is, no, it has nothing to do with undefined, okay, to do with okay? Nothing to do with undefined. What it has to do is with the y values on either side. So let me get to undefined again. It's really hard to hit the mark on Desmos exactly. There's undefined, okay? Y value is undefined right at 0. Limit has to do with what happens near there, okay? So I'm going slightly to the left. Look at the y value. It's really, really close to 3, isn't it? It's a little bit high, but it's close to 3. Now let me go to the right of 0. You can see that value is also really, really close to 3, see? Okay, so when x is close to 0 on either side, y is close to 3. Okay, that's the limit. Okay, that's the limit idea. It doesn't have anything to do with what the actual function value is of 3. Okay, this is important to understand. So again, please ask if you have questions. We good? Okay. I'm going to move back to the practice. Okay, and let's put the chat here. Okay, so let's take a look at this next one. This next one has square roots in it. And you might remember from intermediate algebra, okay, an idea of rationalizing square root. Rationalizing a square root sound familiar? Okay, you might remember when you've got 2 terms like this and one of them is a square root, you can multiply by what's called the conjugate, which is the same 2 terms, but with the opposite sign in between. Okay, if you look at that pattern, it should look a lot like difference of squares. Namely, you've got 2 terms, one's a sum, one's a difference, and it will give you, when you multiply them together, it will give you the square of the difference. It will give you the difference of squares like this. Okay, so that's what I'm hoping you remember. Okay, rationalizing a square root. Okay, so I'm showing you just the numerator here. Okay, haven't done the denominator yet. You might remember, if you're going to do this to a fraction, you need to multiply the denominator by the same conjugate. Okay, in other words, this whole fraction here is just a fancy form of 1 because the numerator and denominator match. Okay, that's what lets you multiply the fraction by its conjugate to start with. Okay, you can't just multiply a numerator or denominator because you'll change the value. But if you multiply by something over the same thing, you're just multiplying by 1. So let me multiply my denominator now. I had an x, and I'm multiplying by 1 plus 1 minus x. Okay, so I'm just multiplying across in the numerator, across in the denominator. And here's where the magic happens, okay? 1 squared is 1. Now take a look at this next term. I have something under a square root sign, a radical sign, squared. The square root and the squaring undo each other. So you're left with minus 1. Okay, here's what you've got. Okay, let's do the squaring first. So I'm left with this. Okay, and then you can see what I have here. Okay, so that's 1 minus 1 plus x squared. So I have 1 minus 1, that's gone. And then I have x squared on top. Okay, everybody see how that's left? Okay, and then down here, you know what? I'm not even really gonna mess with it too much because I have x. Okay, and now look at what happens. Okay, so I'm trying to do the algebraic steps so you can follow. Okay, see anything that factors out any common factor here? Okay, does everybody see that I've got an x by itself down here and an x squared here? So I can get rid of this x, and this is usually the way people do it. They leave the x there. So I'm factoring out a power of x. Okay, now let's let x approach 0. I'm taking the limit, so I'll put a 0 here. Okay, then I have 1 plus the square root of 1 plus 0 squared. Oops. And that gives me 0 on top. And I have 1 plus the square root of 1, which is 1. Okay, so I wind up with a 0. Now, some of you may be looking at that and you may be saying, well, why wasn't it 0 to start with? Because 0 in the denominator means undefined. Okay, if you had plugged 0 in at the beginning over here, you would have gotten 0 over 0. And that's an undefined expression. Okay, so you had to manipulate this algebraically to get an x to factor out of the denominator. So you'd wind up with 0 over something that isn't 0. Okay, so the idea was to, again, factor out. Okay, anybody questions on 19? Okay with 19? Okay, there's no, okay, questions. Okay, you're answering no to no questions. Good. All righty, let's look at 20. Okay, what do you notice here? If I plug in t equals 0, I got a problem here in the first fraction, and I got a problem here because both of these denominators will be 0. So let me ask you, what process would you suggest for number 20? What process would you suggest for 20? Okay, what you want to do is look at the structure of what you've got. Right, you're subtracting fractions. Okay, so if you recognize this expression as a subtraction of fractions, you might say, well, I'm subtracting fractions and they don't have a common denominator. Okay, so least common multiple, least common denominator. Okay, since these are algebraic, okay, let's take a look at it. Let's factor it first. And please remember, I should be writing lim as t approaches 0 in front of all these, but I'm kind of cramped for space. Okay, so let me just factor these for you. Okay, the second denominator factors into t times t plus 1. Okay, everybody recognize that factoring? Okay, that makes it easier for me to find a common denominator. You can see that t times t plus 1 goes into this, and t also goes into this. So my common denominator is simply the second denominator. Okay, so this is my common denominator. But you can see that all I have to do is multiply each numerator. Like, let's see, this is going to be t times t plus 1. I'm just multiplying this first fraction by t plus 1 on the top and on the bottom. Okay, so that's how I'm getting the common denominator. I don't need to mess with the second one at all because it's already got the common denominator. Okay, everybody all right with that? So again, the first thing you want to do is try to get the first fraction to have the common denominator. How do you do that? Well, you multiply by whatever factor is missing, okay? And it's the t plus 1 that's missing. And again, because it's a fraction, you multiply the numerator and denominator by the same thing. That won't change the value of the fraction because it's just a fancy form of 1, okay? Now what we can do is we can do the subtraction. So 1 times t plus 1 is just t plus 1. Bring that minus sign up into the numerator. So doing the subtraction in the numerator, and I'm writing my answer over the common denominator. Okay, so I'm subtracting and putting my answer over the common denominator. Okay, you can see my numerator is t plus 1 minus 1. That just gives me a t on top And here I have t times t plus 1. And lo and behold, I get a t to factor out. Okay, so again, idea was to factor out t. Okay, so that's a good thing. This is leaving a 1 up in the numerator. So now I have the limit as t approaches 0 of 1 over t plus 1. Okay, so if I put a 0 in downstairs, I get 1 over 1, which is 1. So this limit is a 1. Okay, with number 20. Okay, with 20? That was a question. Everybody good with 20? Anybody have any problems with 20? You can see that being able to do calculus and set up for calculus is going to require a reliance on some algebraic skills. Okay, and again, if you're struggling with those skills, please let me know, and I can give you some refresher material. And I would also encourage you leverage some technology. Okay, like I said, there's factoring apps out there. Okay, you can always, like for this one, you can look up sum of two cubes if you remember seeing it, and it'll give you the factoring pattern. Okay. Now with this next one, okay, this is an ordinary exponential. Okay, you can't plug in negative infinity. What this is asking you for is end behavior. Okay, end behavior. As x approaches negative infinity. Okay, so all the way left. Okay, now some people might be able to do this just from what they know about exponentials. So let me ask you, is this a growth function or is this a decay function? Okay, so growth or decay, how do you know? So I'm asking you a question. What do you think? We're looking at 21. Okay. Now I'm just looking at the function y equals e to the 5x. Okay, don't get confused with the limit statement. I'm asking you about the function y equals e to the 5x. Remember, they're not saying f of x equals e to the 5x, but they're asking you for the limit of that function as x approaches negative infinity. Okay? How do you tell whether an exponential function is a decay or a growth function? There's two ways. Okay, first look at the base. Okay, is it greater than 1? Okay, look at the base. Is it greater than 1? What's e? Okay, the base of your exponential is the thing that has the exponent on it. E is a constant, right? It's not a variable. Okay, you can use your calculator to evaluate E. Okay, it's about 2.7. Okay, so E is greater than 1. Okay, and the exponent is positive. Okay, the exponent is positive, 5x. Yes, you can plug in negative values to it, but there's no negative sign on the exponent. Okay, another way you can check is go over to Desmos and graph the thing. Okay, so I'm going to graph y equals 5 e to the 5x. Okay, so here's the graph. Okay, and what this is asking, what the limit statement, you can see it's a growth function, right? So it's a growth function. Okay, so to answer my questions before, if your base is positive and if your exponent doesn't have a negative sign in it, you've got a growth function. If your base is less than, not positive, but greater than 1. If your base is less than 1, like 0.9, okay, you've got a decay function. Or if your base is a number greater than 1 and you've got a negative sign in your exponent, you've got a decay function. Hopefully these are all things you've seen in college algebra. And if not, break out Desmos and graph the thing so you get more comfortable with it. This is an ideal way to play with things. Like, for example, we make it negative. See it flip? There it is again. Okay? Use this tool to solidify your understanding of function behavior. Okay? This is so much easier to use than a standard graphing calculator. Now, what this question was asking, this was a limit statement. It's not asking you for a function value at any particular x. You can't plug in negative infinity. It's not a number. So what you can do is you can zoom way out. Okay, and you can see, what does it look like x, the y values are getting close to way out here. Okay, you can see the calculator is saying 0, but that has to do with the limits of accuracy on the calculator. The x value isn't really 0. It's really, really close to 0. Okay, so essentially you can see, wow, as we head out to the left, it looks like this graph approaches the x-axis, which is y equals 0. Okay, so again, this one I can handle graphically, and I can just say that as I approach in negative infinity, this limit approaches 0. Okay, I'm not saying the function value is 0 at any point. I'm saying as I get way out there to the left on the x-axis, my y values are getting close to 0. Okay, so let me ask you. Okay, with number 21. Okay, this is asking you for end behavior, which you might remember in rational function land is the same thing as a horizontal asymptote. As you get way, way out on either side of the x-axis, what's happening to your y values? For a rational function, that's a horizontal asymptote. Well, this exponential function happens to have y equals 0 as a horizontal asymptote, okay, especially as you go out to the left. Okay, that's all that is. So again, let me put that here. Okay. I want to also show you an example with limits at infinity because the stuff, the material in the text isn't, I mean, it relies heavily on graphical interpretations, particularly for exponential functions. But I want to show you for polynomial, for rational functions. I want to show you how horizontal asymptotes, okay, match up, okay, with the idea of limits at infinity. Okay, so let's just take a look at this last one. This is a kind of like a logistic function. Okay, it's got an exponential in it, and I would recommend again what you can do here if you don't remember properties of exponents. Okay, this much of the exponential here is a decay function, and I believe there's a rule in your notes that says e, as you start approaching really large numbers, you know, as you start getting to like minus infinity. Okay, this is not mathematically correct. It's more correct to say the limit as x approaches minus infinity of e to the x is 0. Okay, so basically as the exponent gets super negative, okay, you can write it like this. Okay, so if your e has a negative exponent and you blow it up, okay, that e is going to shrink. Okay, because remember what this means. This is like 1 over e to the x. If this bottom gets super large, the whole fraction gets really small. Okay, so what I'm doing in this example is I'm blowing up this negative exponent. So this e term is going to approach 0. Okay, and then I'll have 28 over 2 left. Okay, so this limit is 14. Okay, so again, this requires you to remember some properties of powers. Okay, remember a negative power doesn't make anything negative, it makes fractions. And if you blow up the denominator of a fraction, that fraction gets very, very small, right? 1 over a million is smaller than 1 over 1,000, which is smaller than 1/10. Okay, so blowing up a denominator makes things smaller. Okay, so okay with number 22. Okay with number 22. Uh-huh. Good. Let me show you really quick, since you might have missed it in the reading and everything, what to algebraically do with if you've got a function like this. Okay, so limits at infinity. Okay, so let's say we have a rational function, and let's say it looks like this. I'm going to cheat and I'm going to factor it because it's easier that way. Let's see if I can do it in my head and not screw it up. Okay, so I have a rational function. It's got 2 quadratics. Okay, and what I want to know is the limit of f of x as x approaches infinity. Okay, now you might remember it's a rational function, and limits at infinity are asking you about end behavior. As x gets large. Okay, that's the same as asking for a horizontal asymptote. Okay, that's asking for a horizontal asymptote. Can anybody tell me what's the horizontal asymptote of this function? Okay, first thing you want to notice, the degree of the numerator and denominator are the same. So you look for the ratio of the leading coefficients, okay? The ratio of the leading coefficients is what? Not 3. Leading coefficients are the squared terms. Yes, 1, okay? So the coefficient on the x squared in the numerator is 1. The coefficient on the x squared term in the denominator is 1. So the horizontal asymptote is y equals 1. That should be the same as the limit when we approach infinity, okay? Because that means as this graph goes out in both directions, okay, it's going to approach that horizontal line y equals 1. That's the same as a limit. But here's how you do it algebraically. Okay, so algebraically, here's what you do. Divide all terms by the highest power of x. Okay, so I'm looking at that, and that's, in this example, that's going to be x squared, right? So in this example, it's x squared. Okay, so the highest power of x is x squared. So here's what I'm going to do. My limit as x approaches infinity, I'm going to divide each term by x squared. Okay, everybody good with that? Then I'm going to factor out common factors. Okay, so you'll notice in this first one, I have x squared over x squared. Well, whenever you've got a fraction and the numerator and denominator match, that fraction is a 1. The second fraction in the numerator has an x on top and 2 of them on the bottom, so I can cancel out one of those. And there's not much I can do with the last term, so I'll just copy it. In the denominator, I also have an x squared over x squared, that's a 1. And there's not much I can do with the second term because there's no common factors. Everybody all right with that? So remember what I told you about blowing up a denominator of a fraction as 1 over x to the n. Let's put it this way. If I have 1 over x to the n, as this gets large, 1 over x to the n goes to 0. Okay? And again, this is just this is a property of numbers, okay? And you can do this by coming up with examples that kind of make this an idea that's a little clearer. 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000. You can see as these denominators get bigger, these fractions are headed towards 0. Okay, everybody good with that? So that's what I'm doing here. I'm going to take this limit and let these denominators with x's in them get very, very large. So then all of the highlighted fractions will all go to 0. And I'll be left with 1 over 1, which is 1, which is the same as your horizontal asymptote. Okay, so this is an algebraic way to find the limit of a rational function. Everybody good with this example? I'll include it with the notes. Okay. Questions at this point, folks? Again, it's more useful to you if you've got questions to ask them. Okay. So all I did was divide out by the largest power of x, okay, and then took the limit of all the individual fractions, anything that was left with an x in the denominator drops out. Okay, so you can see how you very easily got the ratio of your leading coefficients here. If this had been a 2 and that had been a 1, you would have gotten 2 over 1. Okay, so horizontal asymptote. Okay. How did we get the answer 1? Well, what I did was I divided by the largest power of x, which was x squared. Then I did some algebra. Okay, x squared over x squared is a 1. Whenever your numerator and denominator match, your fraction is worth 1. And then I went and I factored out any x's that were common on the top and bottom. And then I let these blow up. So these fractions with x's in the bottom became zeros. And I'm left with 1 over 1. Okay. Can I scroll up a bit? Okay, let's see. How's that? I don't know if you can see my chat box. Okay. So I don't know if it's in the way or not. But I will definitely share this with the rest of the documents. Okay, so any questions before we move off this example? I realize this was not part of the review, but I thought it was important to share to help you make the connection between horizontal asymptote and limit as x approaches infinity. They're one and the same thing. Okay, and I know lots of times, sometimes instructors don't help you connect the dots that way, so you wind up with this jumble of stuff that doesn't really connect. Okay. All right, let's see if we can, we're already at an hour and 10 minutes, so I want to make sure we can get finished. Okay, so let's take a look at this one. Okay, so let's look at number 23. Now, with these true or false questions, the object is to try to find a counterexample. Does anybody know what a counterexample is? What's a counterexample if you're doing arguments or logic or anything? Somebody says, is this a true statement? What's a counterexample? Okay, well, let's look at the structure of the statement. There's an if part here, and then some conditions, right? They're saying the domain of a function is all real numbers, and the limit as x approaches 2 is 6. So if these conditions are true, the statement says then the function value at 2 has to be 6. So what's a counterexample? A counterexample means you have the same premises. These things are true, but f of 2 is not 6. Okay, so find or build an example where the premises or conditions, I'll call conditions, premise is a logical word, but conditions are true, but the conclusion is different. Okay, build an example where the conditions are true. So our domain is all real numbers, and the limit as x approaches 2 is 6, but the function value at 2 is not 6. Okay, can anybody describe a situation? Okay, when would the limit as x approaches 2 be 6, but f of 2 is not 6? Can anybody come up with an example? This is like that problem in the homework that asked you to draw the graph. Okay, so this is harder than looking at a graph and deciding what the limits are, because it's asking you to construct something. Okay, everybody see what Cecilia is saying. She's saying there's a hole in the graph at 6, but the function value is not, that there's a hole in the graph at 2, but the function value isn't 6. So let's see if I can draw this over here. Okay, and for some of these, I'm going to need to use extra sheets, but okay, so here's x, here's f of x. Okay, here's 2, here's 6. So what Cecilia is proposing is, let's say, as I get close to 2, I'm approaching 6, right? But the function value is some other value. So here's a graph that's a counter example. Okay, so the limit, it's defined for all real numbers. I'll put arrowheads. Okay, so even though there's a hole in the graph, the function is defined at 2. It just has a different value. Let's say it's 1. Okay, and there's your counter example. So you would say the answer to this is false. Okay, because you were able to come up with a counter example. Okay, that's kind of a counter example. Okay, in order to save some time, I'm not going to ask you after every question if everything's okay. I'll expect you to either shout out in the chat or unmute yourself and ask questions. Okay? Everybody all right with that? Okay. Number 24 is going to take some work. I won't be able to fit it here. So I'm going to say see separate sheet. And I will put that on a separate sheet. All right, so here's number 24. Okay, so number 24 is asking us to use the definition of the derivative. Okay, so let me write that down here. The limit as h approaches 0 okay, that's the derivative definition. Okay, that's equaling f of x prime. Right, so everybody see that? Again, I don't know if my control bar is getting in the way. Okay, so you have to let me know if you can't see something. Okay, so here's our f of x. They give us f of x, and it's a x cubed plus 5x plus 4. Okay, so that's f of x. And you can see in order to plug it into the limit definition, I need f of x plus h. So everywhere I see an x, I'm going to plug in an x plus h. Oops. Okay. Right. Now, you can FOIL this out, but there is a pattern actually for cubing things. Okay, and I'm just going to use the pattern really quick so we can save some time. Okay, so there's the pattern for cubing x plus h. And then I have this part. Okay, you can see the 5 would distribute to each of the terms inside. Okay, so there's my expression for f of x plus h. Okay, so now I can put it in the limit statement. Okay, so here's the f of x plus h. then minus the three terms rather, x cubed plus 5x plus. Okay, so this is the numerator of the limit statement. And h on the bottom. Anybody questions so far? Okay, I realize I kind of waved my hands with the cubing. Again, there are algebra apps that will cube. Okay, there are algebra apps that will cube. Otherwise, you've got to do x plus h times x plus h times x plus h, and that takes a while. Okay, so the patterns just help you do it faster. Okay. Now you can see this is going to distribute, and all these terms are going to become negative. So I'm going to wind up with negative x cubed canceling with positive x cubed, negative 5x canceling with positive 5x, and negative 4 canceling with positive 4. So here's what I'm going to be left with. Okay, nothing else there. Okay, everybody all right with the algebra as far as getting rid of the common factors? Okay, so anything I crossed out disappeared because there was a positive and a negative version of it. I'm left with all of these. So hopefully everybody notices you've got an h as a common factor. So I'll factor out an h. Okay, so I've just divided an h out of each one of those numerator terms, and now I can cancel out the one in the denominator. And now I'm taking the limit of everything that's in the numerator. So I'm just plugging in zeros for the h's. Okay, you take the limit, you're just plugging in. You can see I'm left with 3x squared plus 5, because this term drops out and that term drops out. Okay, so I can say f prime of x equals that function. Now remember, this is a derivative function, and what it gives you is the slope of a tangent line to f of x at each point x. Okay, so it's giving you the slope, the change, the rate of change of this function. Okay, notice we started out with a cubic, we wound up with a quadratic. Okay, everybody all right with this one? Anybody questions about this one before we move off of the slide? Okay. All right. Going back to our notes. Okay, the next one says find the equation of the tangent line, okay, to this quadratic. Two separate sheets. Now, if they want the equation of a tangent line, what do you need to find the equation of a line? What do you need to find the equation of a line? You need two things. Anybody remember what one of them is? Okay, this goes all the way back to introductory algebra. This is an introductory algebra question. If somebody said, what's the equation of this line? What would they have to give you? Well, they need to give you 2 points on the line, right? Good, Jasmine. Or they'd need to give you the slope and a point. Okay? If they weren't going to give you a second point. Now, look at this question. You can see we have a point on the line. Okay, so there's our point. What can we do to get the slope? Okay, we're trying to find the equation of a tangent line. How can we get the slope of the tangent line? Anybody? Okay, if you plug it into the equation, that's going to give you the y value. Okay, and you already have it. You know it's 5. Okay, slope of tangent line means what? Okay, y-intercept? No. Okay, because the y-intercept of this function is not going to be on the tangent line. The derivative. Okay, slope of tangent line means derivative. Okay, so let me put this in like this. Y prime equals slope of tangent line. Okay, so if you want the equation of the tangent line, the way you get its slope is to find y prime. And then you can use this other point to find the equation of the line. Let me see if I can do that quickly. Okay, so I'll put another page on here. And so this is number 25. Oops. So equation, tangent line. 2, and f of x is 3x squared plus 2. And it's at 1, 5 is what's called the point of tangency. So that's the point on the curve that you're interested in. Okay? So let's take a look at how we might do that. So here, our x value that we're interested in is 1. Okay, so everybody see that? That's here. Okay, that's our point of tangency. So I'm going to use that in this formula. Okay, so I'm going to get a value out of my slope rather than an equation. F of 1 is 3 times 1 squared plus 2. Okay, so that's 3 times 1 plus 2. Okay, that is 5. Okay, and then I have f of 1 plus h. Okay, so everywhere I see an x, I'm putting in a 1 plus h. Okay, so I'm just squaring a binomial. Square the first term, square the last term, multiply the 2 terms in the middle together and double them. Okay, again, you can use FOIL if you want to, but the pattern is a lot faster. Then distribute the 3. Okay, and then put them into your definition of the derivative. Okay, and remember what I did here. I replaced my x with the given value of x, which is the point of tangency. Okay, so now I'm just putting in these values. Okay, and then the two terms, this was just a 5, right? Okay, so here's the 5 going in here, and here's this part going in. Okay, and that whole thing is over H. Okay, let's see what cancels out. Notice in this first part, I've got a 3 and a 2, which is a 5, and then I'm subtracting a 5. Okay, so this 5 and the 3 and 2 cancel out. So the limit as h approaches 0 of 6h plus 3h squared over h. Okay, then I'm going to factor out my h. And then if I take the limit of this, you can see as h goes to 0, this is going to go to 6. So this is my slope of the tangent line. Okay, and then I have my point 1 comma 5. So find the equation. Okay, and I'm interested in it through the point of tangency. So that's just y equals mx plus b. Put in your m value. And then take the x and y from your point. Okay, so I have 5 equals 6 plus b. Subtract 6 from both sides, right? I get negative 1 equals b. All right, so the line is y equals 6x minus. Okay, this type of a problem is an odd mix of calculus and algebra. Okay, from this point on down, okay, it's purely introductory algebra. What you needed to remember was that the slope of a tangent line is the derivative. So you're using the definition of the derivative to find that value when x is 1. Okay. Questions on this one? Okay. We have two exponential function problems. Now here's what I'll do. I'll include both of them in the notes that I upload, but I'm only going to be able to do one of them now. Okay, so let me just do 26. Okay, and then that way you can look at 26 and 27 in the notes and understand what's going on. Okay, so going back, let me show you. Okay, it says over here, the average cost of an electric toothbrush was $78.50 in 1976. The same kind of toothbrush on average costs $10.99 in 2018. So you can see the price is decreasing. So let's assume we have an exponential decay model here. Find the function that models the cost of the toothbrush and then use it to make a prediction. Okay, what will it cost in 2025? Okay, so we're going to do this one really quick. So first, build the model. Then use it to predict. Okay, then use it to predict. That is exactly what you would do in real life. Okay, so I'm going to go to a separate sheet. All right, and let's work on this one together. All right, so this is 26. Okay, and here's what they gave us. They said it's an exponential model. They're saying cost was 7850 in 1976. Okay, so we're building a model. Okay, so we can say C of T equals 7850 in 1976. Now, when you're building a model, usually let your earliest year be your 0 year. So we're going to say T equals 0 in 1976. They also tell us C of T equals 1099. How many years later? Okay, in 2018. Okay, well, that's, believe it or not, that is 42 years later. All right, so does everybody understand the idea of using a 0 for your independent variable? You're not going to put in 1976, 2018. You're going to call the first year 0 and then count up from that. Okay, so 2018 minus 1976 is 42 years. Okay, so this actually gives you a 2 ordered pairs, right? It gives you 0, 7850, and 42, and 99. Okay, where this is a T and this is a C of T, like an X and a Y, or an input and an output value. Then you've got to remember the format for a model. Okay, that's C of T equals your starting value, which I'll call A. Sometimes they call it A sub 0. Okay, that's your basic template. Okay, so this is exponential template. Okay, so here's my starting value. Okay, that's my 7850. So I just plug that in. Okay, then what I'm going to do is I'm going to use my second point, which has a T value, okay, and a C of T value. And I'm going to plug it into my model equation to try to figure out K. Okay, now what K is K is your decay rate. I'm having some problems with my spelling since I'm Russian. Okay, decay rate. It won't take too much longer, don't worry. Hang with me, folks, okay? So I'm going to put in 1099 equals 7850 e to the k times 42. Okay, I'm just plugging in those numbers. First thing I'm going to do, I'm trying to isolate k. So I'm going to divide both sides by 7850. I'm not going to simplify anything, okay, except to get rid of that. So here's what I've got, 1099 over 7850 equals e to the 42k. I just switched the order there. Okay, so now I've got an exponential function. I want to get k out of the exponent. How do I get k out of the exponent? How do you get k out of there? Anybody know what to do next? How do you solve an exponential, folks? Use the natural log. Yes. Okay, you're using the natural log because your base on the exponential is e. If your base was anything else, you might consider using the common log. But I'm going to take ln of both sides. Okay, and to take ln of e to some exponent is just asking you what's the exponent. Okay, so that's what pulls that exponent out and puts it down where you can actually solve for it. The last thing to do is to divide both sides by 42. Okay, and this will give you k. And this is something you would evaluate on your calculator. Okay, and again, please make sure you've got parentheses in the right places. All right, and I got approximately negative 0.0468 to be K. Okay, round K to 4 decimal places. So now use your model. Okay, here's your model now that you built. Cost is modeled by 7850, my starting value, e to the minus 0.0468t. So what this is saying is every year, okay, the price of this electric toothbrush drops by about 4.5%. Okay, see the negative 0.04? That's your decay rate. Okay. So now you want to use the model to figure out what the cost of the toothbrush would be in 2025. Okay, and remember we started with 1976, so T would be 49 in that year. So you're just going to evaluate C of 49. This is strictly a calculator problem. Okay, and again, hopefully everybody has a decent calculator. If not, a good calculator. I think I may have shared this with you already. A good online calculator is Web 2.0 calculator. Just search for Web 2.0 calculator, right? It'll actually display something in mathematical notation before you hit enter, so you can see if your parentheses are right. Okay. So when I did this, I got, and again, I'd round this to dollars and cents, okay, because it's a cost. Okay, so in 2025, this toothbrush price should be down to $7.92. Okay. What is important about this example isn't so much the fiddly details about what the answer is, but the process. First, build the exponential model from your given data. They gave you an initial value, and they gave you one other point. Okay, so you use that second point to figure out K, and then you use your specific model, which is this one, to actually answer the question, to actually make a prediction. Okay, so let me ask you, are you okay with this process? Okay, and this process is not just true for exponentials, it's true for a lot of modeling, okay? Okay, very quickly, I want to talk about drawing a derivative graph from another graph. Okay, let's take a look at this one. They are given a function over here that kind of looks like a cubic, all right? And what you want to realize that you're drawing when you draw the derivative graph is you're drawing the slope of the tangent line. Okay, so slope of tangent line is the y value. Okay, so the first thing I would suggest you do with your graph is find the places where the slope is 0. That's going to be these two turnaround points. Okay, this example has it at 2 and at -2. So the slope of your tangent line is 0 there. So go over to your derivative graph, find -2 and 2, and put a dot right on the x-axis. Why is that? That's where y is 0. Okay, and remember, y is tracking the slope of your tangent line. All right, so slope is 0. Everybody good with that? Then what you're going to do is look at this graph and decide, is the slope of the tangent line positive or negative here? Well, leading up to that first 0, the slope is negative. That means your y values will be negative here. Likewise, on this side, okay, your slope is negative. So going away from the second point, your slopes will be negative. Okay, again, having issues with drawing, but that's okay. And again, you can see, well, if that's cubic, this must be quadratic. And you've got a quadratic graph. Okay, but the idea is graph the turnaround points first. Okay, and their x-intercepts. Okay, that's the trick. All right. So we've run over, well, actually, we're supposed to take an hour and 40 minutes for this class, but I ran over a bit because I wanted to make sure you got your questions answered. I'm going to stop sharing. Okay, anybody questions about 28 or anything else I'm sharing? Questions on the review? And I will upload everything, don't worry. Questions? Okay. I will stop sharing and come back to the meeting. Okay. Can I review number 28 again? Sure. Okay, let me share that one. Okay, that's this one. Okay, everybody can see it. All right. What I am tracking over here, and again, I gave you an applet, okay, I think it's in week 3, that will track the derivative as you move across a graph from left to right. It will actually draw you the derivative. What the y values of your derivative are the slopes of these tangent lines. So the first thing I told you to do was find out where the slope of the tangent line is 0. That's going to be where it's horizontal. Okay, so I found those two x values. They're at 2 and -2. So I went over to my derivative graph and I put those on the x-axis. How come? Because that's where y is 0, right? Then I'm looking at the slopes on my original function, and I can see the slopes are negative going to that first horizontal slope, and they're negative going away from the second one. So that means the y values have to be negative. So negative slope translates into negative y values. Okay? You can see in between the two horizontal slopes, okay, I've got positive slopes here. So I've got positive y values over here. Okay, does that make sense? Anybody have any other questions about 28? Okay. All right. It is really, really important to understand what a derivative function is giving you. Okay. So I would encourage you to please play with that app that I put in our Canvas course until you're comfortable with what it's showing you. Okay, a lot of students just go through the mechanical manipulations, but they don't have a really strong understanding. Yeah, the notes will be in the files along with the video, absolutely. Okay. So let me ask you again, any questions either on the review or on the exam? Do you understand what's expected? Okay, for those of you who might have joined late, okay, there are directions for the exam. There's 13 questions. You've got an hour and 40 minutes, which is about what we took reviewing everything, okay, with more than twice as many questions, okay? And basically, you will upload your work, okay, to me, okay? You're going to send me your work so I can go through and regrade it. So let's say you take the exam and you don't do as well as you thought. As long as you show me work, please not scribbles, okay? Try to work out each problem neatly enough for someone else to follow you, okay? I can give you partial credit, okay? Maybe you just made an arithmetic mistake. Will there be second chances? No. Okay, so try to do it as well as you can the first time. And remember, I'm generous with partial credit. Okay, so please try to show me your work. Okay, this is an opportunity to show what you've learned in this first unit. Okay, so any other questions? Any other questions? Okay, again, if you have questions once you attempt the exam and you're not sure what's going on, okay, again, I'm not going to help you with the problems, but I can certainly help you if you have technical issues. Some of you have had some technical difficulty this week. I'd be happy to help you with that. Okay, so if there are no other questions on this, that's all I have for today. So I'll stop recording and feel free.